again. And yay, we did it. Okay, sweet. Yeah, I'm not muted. I was thinking I was muted for a second. Okay, sweet, we're back. And keyboard shortcuts are working, so that's pretty cool. Oh yeah, there's this cool thing. I thought it was cool. This neofetch thing, I've never tried that before. It's kind of cool. Gives some interesting little details there about the system. Not bad. I like it. And they do it for Linux and Windows and all that too. Kind of cool. All right. Can is open. And here we go. Why did the mouse just do that? That was really weird. Okay. So that's going to distract the shit out of me if I leave it up on my terminal. So let's do this. Okay, cool. And we're back. And we are going to do this. Yeah, we're going to impulse several traits to give this some more functionality. So just to go over what we started with, we have a basic RingBuffer. We have our struct that keeps our main public type, and in our impl we have a basic function allocate. That's a private function, private method, and that's actually handling our allocation for us. We are just allocating right away instead of waiting. A lot of data structures seem to not do that, but I guess if you used with capacity on a vec in Rust, I bet they're allocating right away. That would actually be an interesting thing to find out. Shall we? Why not? Let's take a look at the vec source code. Okay, let's do vec, and we want with capacity. Really? Why didn't that work? It's right there. Unbelievable. I think my mic might be a little bit hot. I'm gonna try turning it down because I keep hitting. I'll just go the tiniest bit down. See how that is. Hopefully not too low. Okay. All right, so let's look at how constructs a new empty vec with at least the specified capacity. The vector will be able to hold at least capacity elements without reallocating. This method is allowed to allocate for more elements than capacity. If capacity is 0, the vector will not allocate. It is important to note that although the return vector has the minimum capacity specified, the vector will have a 0 length. For an explanation of the difference between length and capacity, see capacity and reallocation. Obviously, we understand that because it's just an array list and they're talking about the underlying memory allocation versus the actual data structure of elements that we care about. Okay. For vec of t, where t is a 0 size type, there will be no allocation and the capacity will always be u size max. Yeah, I knew that part. So it sounds like they just do an allocate right away. So this does a self with capacity n. Let's see if we can find this function. with capacity n. I'm guessing we don't have any special IntelliSense stuff going on here. Okay, maybe it's further down. With capacity n, capacity global. Okay, so static method. Okay, here we go. It's in the allocator implementation. That would make sense. There it is, with capacity n. Okay. Let's see what they have to say about this. Okay, that's the same docs as we read before. And then this just does a raw vec with capacity and capacity alloc. Okay. And if I remember right, I think raw vec might even be here. I guess that doesn't work. You have to use this. Oh no, it's in a different crate. Okay. I think it's pretty safe to say that they are allocating right away, because otherwise, well, I guess even with zero allocation, it's still getting a pointer. Okay, let's look at the raw vec if we can. What do I want to do? I want to go to the source code. Thick. We're making it thick, Dylan. Hey guys. I didn't notice that chat. It could have been there for a long time. I was on a random thought train here and looking at source code. Yeah, Scott. Well, you know what a ring counter is. Well, you got me on that. I don't know what a ring counter is. All right. Let me look at what a ring counter is. Good times. Ring counter. Oh, okay. Yeah, very, very different. A ring counter is a type of counter composed of flip-flops. So it's composed of sandals, is that right? What, the ring counter? Is that what you're talking about? That's what it is? I don't know. Let's see. Or are you talking about what a ring, explaining what a RingBuffer is? Oh yeah, it's pretty close. I mean, you could do it with a doubly linked list. It would just not be. That's not usually how people do it. They do it with like a raw memory allocation or an array. You could just call it an array underneath. And I just mean unsizable, a fixed size array, fixed size memory buffer underneath. But everything else you said is right. Yeah. Yep. It's contagious. It's a contagious memory block. It's just a U instead of the I on your most recent spelling. Well, you know, instead of the second I. I believe that's how it's spelled. Yeah, I don't know what this is, but it might be. Okay, straight ring counter, also known as a one hot counter, connects the output of the last shift register to the first shift register input and circulates a single 1 bit around the ring. Okay. So, okay. Finite state machines, yeah. Okay. A binary counter would require an adder circuit, which is substantially more complex than a ring counter and has higher propagation delay as the number of bits increases. Yeah, I mean, in a way, they seem similar. Yeah, cool. Ring counters, good times. Yeah, so we finished our RingBuffer, like a really basic one yesterday. So I'll just show you guys. and I'll get back to the source code in a minute. That is the source code for, I was looking at the way VEC is implemented in the standard library. So we basically just started with a pointer. We have a head, a tail, a capacity for the underlying memory allocation, and then a length. Head and tail are basically just indexes into the array or the memory buff. Yeah, exactly. So we talked about yesterday some really good examples of where this is helpful. So one example is like video buffering, right? So when you buffer video, sometimes you drop frames. And so what happens is what you care about the most, right? If a frame drops, is to still just get to the most recent frames that are available. So a frame drop is kind of like, you know, at some point, somewhere along the way, right? Somebody wasn't fast enough to catch all of the frames. So in that case, it's like this sliding window, and that's why I keep going like this. It's also a Tai Chi move. Not exactly, but it kind of feels like it. Yeah, so I thought that was a pretty good example. And if, you know, the most recent data, if you're at capacity, will overwrite the oldest data, right? So, yeah, you got it, Scott. I think you've got it. So, and it's fixed size, right? So we just have this single allocation that we can do right on our constructor. It would be more rusty to not even have a new on here and just have this called with capacity. That's usually how Rust does it. And then, yeah, so here's our push front, which kind of shows the whole overwrite behavior. So this is just getting where we want to push the value to. We check if it's going to be an overwrite. The main reason we check if it's going to be an overwrite is because this is just like a extra memory, making sure we don't have a memory leak in our program. So if I'll explain that in a second, because it's not really about the basics of this. But here I'm just writing at this point, and that point might be the current tail, and that's actually what we check for down here. So actually I was going to change this now that I remember. Now that we're here talking about it, we can change this to is overwrite. So we already overwrote the current tail in memory, and so now the new tail is the element that was before the tail. Since it wraps around, that's kind of why they call it a ring, right? Before could end up bringing you to the end of the array, and that's why there's the before method here, just as a helper to help us wrap around. So yeah, that's push front. Pop back is a little bit simpler, kind of what you'd expect. You're really just finding that tail and popping it off, right? Similar to how you would do it on an array list or anything like that. I'd say the only difference here, of course, is this. Let's see, let me think about this. Yeah, old tail, and then wait, why did I do this? Hold on a second. I feel like I did something wrong. It might be a bug, you know, reading the code the day after, right? Let's think about this. So we get the index that we want to read, and then in which I don't understand why I would only be updating tail to tail -1 if self.length is great. Oh, if self.length is greater than 0. Nope, I'm just being dumb. Sorry. That makes perfect sense. If we don't have any elements, or no, actually what this case is, yeah, it compiles, it works, it passes the tests. So yeah, that's what it is. No, I just don't know how to read. So we decrement the length here already, and this is just the case if we only had one element left after we pop this current element off. We don't actually, let me think. Right, if this is the last element we're popping off, sorry, that's what I was trying to say. Then we don't want to do self.before. We don't need to do that. Because now self.tail is just going to be none. Which is already done implicitly. It's a little more advanced Rust code, but it's done implicitly in this self.tail.take actually sets self.tail to none. And so this is just making sure that I don't end up updating self.tail to a pointer in memory that actually doesn't contain a value that we care about at this point, because we don't have any actual elements allocated. I don't know if I explained that well, but that's that. That was to fix a bug, now that I remember what it was there for. So yeah, just to go back up here and explain this part, this is just the case where the elements in our list, in our buffer, the T is drop. So if it needs drop, we need to make sure that we actually drop it. Otherwise, for instance, if you had a list, or if you put boxes in this RingBuffer, let's just say, and a box, you know, is a kind of smart pointer. It points to another piece. Well, it moves something from the stack to the heap, right? And so we'd have the box actually in that contiguous memory thing, but it'd be pointing to another place in memory. If we didn't call drop on that, the other place in memory would never get deallocated and we'd have a memory leak. So that's the point of that code. So that's that. That was push front, pop back, constructor. We have a drop implementation. It's pretty standard. It's kind of similar to the whole if T needs drop, we call drop on it. And then we dealloc our actual memory buffer when we're all done. We wrote a couple tests. We wrote one with an isize, and then to make sure that we didn't have a memory leak if T is drop, we did a RingBuffer with boxes. And all those tests pass. We did make that one change, so let's just double check that I didn't randomly break something. Looks good. Looks good. So yeah, thanks for the questions. Let me know if that made any sense. What I wanted to look at real quick, what I was in the middle of, is I wanted to see if in the standard library they use a raw vec under vec and under vectq to handle the manual memory allocations. It's just like an extra abstraction. It's kind of like, you know, the contiguous memory buffer, right? That's what raw vec is. So I just wanted to look at oh, okay, this is cool. So I can actually jump around here. So where's raw vec? Create raw vec, raw vec. Okay. Maybe it's in here. No. Let's see if we can find it. Vec mod. Okay, it's not there. Don't think it's gonna be. Oh, there it is. Raw vec. Sweet. So here's our raw vec implementation. And what I wanted to look at is when it started with the capacity, what happens. So it's going to be in its allocator and pull with capacity n, self allocate n, capacity, alloc init, uninitialized, alloc. Okay. So this is an enum, I would guess. I think we saw it up here. The contents of the new memory are uninitialized. The new memory is guaranteed to be zeroed. Okay. So let's look at with capacity and allocate in, right? So let's look at allocate in. There it is. It's not too big of a function. Allocate in capacity init, and that's just uninitialized, and alloc a. I don't remember what the alloc argument was up here. It's just the alloc, which was passed to it from vec. Okay, I don't remember what that is, so let's just open this up, separate tab, and look at it here. Lots of smooth scrolling just to trigger people. Oh, okay, right. It's just the global allocator. Right. I forgot. So it's just the allocator. A. I get it now. The standard allocator in Rust. Okay. Allocate in. Here we go. Let's read this code. So if we have a zero size type, it's just going to not allocate because there is not anything. Else. Okay. Cool. Let layout match layout array t capacity. Okay, layout. Okay, so right, since layout array returns a result type, it's pattern matching on that result, making sure there's not an overflow. And then alloc guard is doing, I don't know what alloc guard is, but that's fine. We can skip over that. Let result equals match init alloc uninitialized alloc.allocate. Otherwise, alloc allocate 0. Okay. Let pointer equals match result. Okay. So they do in fact allocate when you call with capacity. That is what I expected. Cool. That's what I wanted to know. So we are matching very close to what the standard lib does, at least in that sense. I'm just going to double check my suspicion while we're here. That vectq, which is a RingBuffer, except it's actually growable, so pretty interesting. Does not actually have. Okay, so they do have the option to. I remember I read this, I think, the other day. You can create an empty DQ if you want to. And if you created an empty DQ, you're not going to allocate. And then you just have vectq with capacity. The reason this doesn't make sense for our implementation is because their ring buffer is growable and ours is not, which is a little bit more traditional to have a non-growable ring buffer. Okay, cool. I satisfied my curiosity there, and we can move on. So we have push front, we have pop back. One of the things I wanted to do is do a deref because I thought it'd be kind of interesting. A deref for a well, this is partly what makes a ring buffer interesting. Is that although we have an underlying contiguous memory buffer, the elements that we add to the ring buffer aren't necessarily in contiguous memory. And that's because a ring buffer wraps. So we went through some examples the other day that this is a valid ring buffer because of the wrapping, and these would be like the indexes that you actually care about as the user as far as elements that you actually added to them. So you might have something like 4, 5, XXX. Those are parts of our contiguous memory buffer that are unused currently. And so our head in this case is at index 5, but our tail is at index 1. And so that's why you can't say that these are the elements that we've added are in contiguous memory. So I'll just leave this here while we're implementing deref, because I think it'll also, I believe you write it like this, but I could be wrong. Maybe it's just, no, I think that's just my return type. Let's see. Yeah, it might be. It might be. It might be right. Did we impl deref for stack? I don't think we ended up doing that. No. So by implementing deref, what we're basically doing is we're saying you can take all of the values that we have and you can actually put them into a slice, which gives you a bunch of special methods that you can use because you derefed it into a slice. So that's the main reason that I was doing that. Let's see. So what's interesting is it doesn't look like vecdq implements deref, which could be because of the non-contiguous nature of it. And it could be that we're getting into a space that's going to be really hard to manage. But that's cool. We can do that. we can manage that. Funny. Yeah, I don't see it. So let's just look, and just kind of for understanding. So if you look on the left hand side here, these are the methods that are in the vec impl, but these are the methods in deref, which are actually a hell of a lot, because essentially these are all the things you can do with slices. So if we can successfully impl a deref target to slice T, we can get a lot of free stuff, which is pretty cool. So we'll see if we can. So let's do RingBuffer, and we're gonna reference, this is a reference implementation of VEC that we took from Astronomicon. So it's kind of a simplified version of the standard library that's a little bit easier to understand. And this actually explains partly like how you would do it for an actual VEC, which is since you have a contiguous memory part, you have contiguous memory for a VEC, you can actually just do a std slice from raw parts, and it just grabs all that memory and gives it to the slice. So I don't know exactly. I mean, my naive way of thinking about it is maybe I could give it a slice of two different places and then kind of concat them together in some way, but I don't know if that's actually going to work. So anyway, that's that. So, right, I did write it wrong. That's mostly why I wanted to look at that. Where are we? RingBuffer. Let's go. Okay. So that's what it is. Okay, so we're gonna say type target equals T, and then pub function deref, and deref takes n and self, I believe, and then returns a slice of T as a reference. Don't need that. And do you not need pub for this trait? That might be what it's telling me. Unnecessary visibility qualifier. Okay. That works for me. So we're just going to have to look at what is possible. Now we have a trick which we know is going to work, which we could say if self.head is less than self.tail, then unsafe std slice from raw parts. Yes, yes. Data, so we need the pointer and then we need the length, right? So to get the pointer of head, we have to say self.pointer.asPointer.add self.head. That's not going to work because self.head is actually an optional. I wonder how this works in the sense that what if that's none? Let me just think about this. Okay, yeah, I think that's what I want to do. So I wonder how I can just return like an empty slice. That would be interesting. So let's start with if self.length equals 0. I don't know if this will work. Return that. That's technically not real I don't think that works, but we'll see what happens. Oh, I didn't import dref. Let's see if we can get the LSP to do it for us. And yep, that one. No, I pressed the wrong button. I was supposed to do tab. Let's try this again. I don't use the LSP a lot. Beautiful. It worked. Okay. What, you can't put X's? Oh, it's just an old thing. Okay. Here we go. I like this. Oh, you already hate this? Oh. Classic. Okay. So it might tell me that that return is wrong. Let's do implicit returns for now instead of the early thing. Okay. If self.length equals 0, now are you saying that it's a mismatch type? Expected unit type, found reference. Expected this to be a unit. You did. Is that because of this down here? Let's just delete this for now. See what happens. Okay, it isn't complaining about that anymore, which is good. This is probably not working because I'm... Oh no, it's just about this whole block of it not working. That's fine. Okay, let's fix this and then we'll worry about that. I can't remember if you can compare options of the same type. Like, does option impl EQ if T is EQ? It might. It very well might. I usually have 3 or 4 regulars that are just not here the last couple days, which is fine. I know people have other things to do, but it does make me think, like, did I say something like terrible the other day and just not realize it? I don't think so. It's possible. I'm not always a nice person, but I don't think I did that. It's probably just coincidence. We'll go with that for now. Anyway, self.pointer as pointer.add self.head. Okay, that's not gonna work. Okay, we already know that self.length doesn't equal 0. So in that case, self.tail and self.head should be safe to unwrap. So we're just going to do that here. And then we are going to put in our length as the slice length. And let's see what it hates about us now. A lot of things, apparently. That's okay. Expected and T found unit. Where? How? If expressions without else evaluate to... Oh, because I never put an else. That's funny. I didn't know that. I've never hit that error before. New error. It makes sense. It's not exhaustive pattern matching, right? So if you're returning a value that you care about, it's kind of saying you're not handling this case here. So let's see if we can just return... Oh god. Let's see. I know how to type. There we go. Let's see if we can just return this here. And then see where we're at. Okay. It might like us. Doesn't mean we did it right because it's unsafe, right? We could have really fucked it up. But it is at least happy about it from a type and borrow checker perspective. It's nice that I can actually just return that empty slice and it just does the right thing. So that makes it feel pretty good. I am kind of, oh, I thought through it. At first I was kind of confused about this vec implementation because I was like, well, what if the length is 0? But because they're doing from raw parts, if the length is 0, and because they start, because, what am I trying to say? Because the vec is adding things to the end and self-dot pointer in a vec is the head, then you know that you're just going to start at the head and go to length. And we just don't have the same assumptions for our ring buffer. So we know that we can do this. But obviously that is only halfway there. We need something better than this. Let's start with what we have though, and do this, which of course would not work. We would end up with multiple problems, right? We could end up getting out of bounds. We could be reading we could be just reading empty data, empty blocks that we have in our allocation, but don't actually have the types that we want. Don't have any meaningful data. Basically, it wouldn't return all the elements that we want. So what we want to do is slice. So if, let's think about this. If head is greater than tail, first of all, it's really cool that option just imples eq. That's really cool. I mean, I just haven't had to use it explicitly before, and it's really ergonomic that way. I don't have to unwrap anything. It's just automatically doing it for me, which is really sweet. Cool. So we're going to want to slice from head to end. That makes sense. But we would have to determine end. Well, really, we just need the length from our head to our end, right? So if we slice from head to, let's see, capacity minus head. So in this example here, head is at index 5, and our capacity is it 9 elements? Yeah, our capacity is 9. And so we would want to read 4 elements. Yeah, so capacity minus head works. Okay, so if we slice from head, capacity minus head, that should work. And then for the tail, that means the tail has wrapped around to the beginning. So then we would want to slice from pointer and then tail. Let's see, since we're 0 index, tail plus 1. Yeah, I think that would work. Okay, let's try that out. Let's just start with our slices. I'm gonna add this as our return for now, just so we don't get type errors to begin with. let head slice equals, this should go here, and then we're going to say let tail slice equals stud slice from raw parts. Excuse me. Sorry for the big breath into the camera. Camera? Oh my god, microphone. Stud slice from raw parts. Self dot pointer dot as pointer. Yeah, that's right. To self dot tail dot unwrap, unwarp it, unwrap +1. Forgot the semicolon, so that's why we're getting that. And that looks good. Okay, so now we have to see, can we, with a slice, concat or something. I don't actually know. I don't know what we can do yet. Let's look at stud slice. Okay, there's an experimental concat. Performs a slicer from a pointer and a length. Okay. Huh. Well, that's not what I was hoping for. Let's just see what this does. They don't even have it documented, really. Oh, this is the trait. Oh my god. Sometimes. Flattens a slice of T into a single value self output. Oh, that's not what I was expecting it to do. Flattens a slice of T into a single value self.output. Okay. That's that. Let's look at this again. Let's look at from raw parts. Forms a slice from a pointer and a length. The len argument is the number of elements, not the number of bytes. Yep. Oh, okay. Well, there you go. This is why you can't do it. And this is why standard lib doesn't implement dref. Oh, I forgot to switch. Sorry, guys. Slices can never span across multiple allocated objects. It makes sense conceptually, I just wanted to try it. Yeah. Oh well. We don't get all of our fun things here for doing dref. That's all right. We tried. It's an interesting idea. So let's just here. We'll actually commit this just to keep the code somewhere. RingBuffer dref not possible. Okay, that's good. And then we'll go ahead and delete that code. And let's figure out what we want to do next to get actual iter type functionality on a vectq. Or I could say our RingBuffer. Okay, give me a second here. Quick message check. Okay, cool. That's good. All right, sick. All right, let's get back into the code and think about how we're going to do this. There's a couple things that they do in vectq. You can do a from vec and like into vec. So I think that's interesting. Well, let's just look. Let's look at the interface over here for a minute. Do a from iterator. We could impl index. It's not a bad idea. It's not a bad idea to just impl index. Function index. What does IndexMut do? Performs immutable indexing operation. And then, of course, there's like into iterator, to iter self. Okay. Huh. Okay. Yeah, let's do index. I haven't done an index implementation yet, so might as well. Might as well. That'll give us some interesting capability. One momento. There we go. All right. I think I'm good. Okay. So we're going to impl t index for back to q. That's that's not gonna work. For didn't change my scene. RingBuffer t. And we have to define our output type, which is t. And then we have function index, takes a reference to self and a use size, and returns a t. Okay, getting somewhere. And then basically given an index, we need to be able to get it. So this is where we have to translate our, this is where we have to translate our RingBuffer index to our allocation index. So this is where math is helpful. So let's just talk about this real quick. If we have index 0, like we'll just use the above example. So index 0 is easy. Index 0 is just our head offset, right? So if 0 equals head, guess I need to write these in comments so that the this whole thing doesn't piss me off with the indentation. So 0 is head, 1 equals head plus 1, of course. And then you know, it keeps going, right? 3 would equal head plus 3, right? And using our example 6 lines above. Now the thing is that 4 would end up wrapping. This is where modulo kind of comes in. I just have to think of what the actual, like, how do we get 4 given our head position and our capacity, right? So I wonder how index actually handles. I don't actually know how index handles if somebody passes a out of bounds index. I'll have to look at that to see what we're supposed to do in that case, since we're not doing an optional. Maybe it doesn't matter. I don't know. We'll have to see. We'll have to see how that works. Okay. So to get to index 4, if it was at the beginning of the array, we have head and capacity. What would we actually do? Like, I know to get to tail, I can just do a modulo. Like in this case, oh, this is what I need to do though. So head plus 3, which equals, in this case, 8. So head is index 5. This is 6, right? And then 4, you could say is 9, right? But that's where modulo comes in. Because if I say 9 modulo self dot capacity, that would equal 0. That's it. That's pretty awesome. Yeah. Okay. That's it. So we'll just call this offset equals since I don't know yet how this works, we're just going to unwrap head until I know how to handle errors. But basically we're going to do head.unwrap plus index modulo self.cap. And that gives us our offset. And then to actually get our T, we just go into unsafe and we say pointer read. I'm not sure how to handle the lifetime part of this, but we'll get there. Self dot pointer dot as pointer. At least we'll have the basic like code that we care about. So this is going to be a T, but we need it to be that. I don't think that's going to work off right away. Well, we'll see what happens. Okay. So index has to be given use size, I'm guessing. No? Oh, I didn't. Nope, I'm just dumb. Classic. Didn't import. Okay. That's that. And then we'll just do this. And then index does require a thing. Like that. Okay. Cool. So I like this, but I'm sure it's going to say that this doesn't live long enough. Yeah. Temporary value created here. Blah, blah, blah. So what can we do? I guess what I'm wondering is, not sure. I just need to think about it. Okay, so we don't need this anymore because we figured that out. But of course, this isn't going to work. I wonder if there's anything else in Pointer that would give me something good. Oh, interesting. So maybe I want from raw parts. Huh. Const function t2 const t. So it's from ref. Okay, no. Let's see. Function const t, ts.t, metadata. I don't know what the metadata is really about. So read gives us the actual element. I think that's kind of the problem. Now I can do slice from all parts, but I don't think that's what I want. Because I'm still... Okay. Interesting. Okay. Oh yeah, we don't need this whole line right now. So let's try asking GPT. We'll see what's up. See what's up in the GPT land. There we go. Okay. And what are we checking? We want to say, how do I get a reference to a pointer. Maybe that's my answer right there, what I just read out. Okay, so I have a raw pointer, this much we know. And if I want to go raw pointer, oh, so it's just built into the raw pointer. That makes sense. Now, can I just pass this as ref, like here? Like, can I do, let's just do this. When I just wrote that GPT question out, I realized how dumb I was being because I already have a pointer. Like the pointer is here. And so, okay, self.pointer dot as pointer gives me a mute t. It's possible that non-null just has an as ref, which gives me an and at, yeah. I think that's our answer right there. That's really nice. That's really nice. Now, the only problem is, of course, we didn't use our offset. So I do actually have to do this thing. Add offset dot as ref. But now you don't like it. Why don't you like this? But you liked me before. Expected reference and t. Found enum option and t. Interesting. Okay, so when I do add, what do I get? Okay, I get a self back, and a self should be a mute t. So when I do an as ref, okay, then we do that. Okay, so this isn't handling null pointers is really what it comes down to if I just unwrap it. Cool. I like that. That's not bad. Now we just have to actually look at what we're supposed to handle when we impl index, because I don't actually know. So let's find out. Just because I don't know how we're supposed to handle it, like, does it just like guarantee that I'm not going to get an index that's out of bounds? In that case, it is safe to unwrap, but I don't know if that is the case. So we'll just see. Sorry, quick message check here, and then we'll get back into it. Hope the day is going well for everybody out there in the world. Okay, cool. So let's look at index here. Yeah, it's readable enough for you folks. So we have type output that has to be sized. That's fine. A required method. Function index. Container index is actually syntactic sugar for deref container.index index, but only when used as an immutable value. If a mutable value is requested, IndexMut is used instead. This allows nice things such as let value equals v index if the type of value implements copy. Interesting. As a read-only nucleotide count container, enabling individual counts to be retrieved with index syntax. Okay. Well, that's interesting, but I would like to see something a little bit more interesting. I guess that's not going to happen. Okay. Huh. Impl index range use size for string output stir. Does that like get a just part of a string? I guess that's how it works. That's how all that special index stuff works. So I'm just gonna do index for use size because that's what vectq does, and I think that's the thing that matters the most. Yeah, I think that's cool. That's what we're gonna do. Okay. We're just gonna keep what we have, and then we will take a look at, we'll test this out. Let's do this guy. So before we pop anything, well, this is mostly what I'm wondering. Well, we'll do a happy path, and then we'll see what's wrong. Assert EQ and 15 R0. Not how it works. Cannot compare and iSize with iSize. Oh, I'm confused. Oh, is that because even though I pass it a reference, it actually just copies it? Oh, that's right. That was the point of the syntactic sugar. Is that what's actually happening is R0 copies what's underneath, which is pretty cool. Hey, look at that. That's not bad. Implementing index. Pretty sweet. Okay, so what I don't understand, I guess it's on the caller's responsibility to not do this, like before I pushed anything. See, what sucks about the docs in this case is they showed me an example. Well, let's see. Match nucleotide. Let's go back to docs. ACGT. I think this is too confusing of an example. But, okay. Nucleotide count is the actual struct that they implemented it on. And then it's self.a. Oh, okay. I get it now. I get it. The thing that sucks about this index thing, I mean, that's cool and all, but like it doesn't show me if something's out of bounds of what I'm supposed to do. So let's just go ahead and look at the impl use size for vec maybe, and see if that is understandable. Might not be. Index, index, and star star self index. Okay, well that's really helpful, isn't it? Oh god. Okay. Let's ask this question to GPT. How could we implement index trait for an array list for our custom array list? Yeah, that's not helpful because it's underneath. Okay. Write a stack using unsafe. How about that? Oh my god. Did it really just do data vec new? Oh my god. This doesn't use unsafe. You didn't use anything that's unsafe. Oh my god. Okay. When implementing index trait, how do I handle out of bounds indices? Okay. It's hilarious because that's not what they did right here, as far as I can tell, in self.git. Yeah, I don't think that does what they thought that it was doing. I guess we could actually do this similar thing, since what we do returns an option. We could just throw an expect on there, and you can do a result. But this isn't even. Oh, I see. Because you can define that your output is a result T error. But since vecdeq doesn't do that, I guess I'm not going to do that. I'm just going to stick with what I have and then write a panic. I think that's fair. So instead of an unwrap, we will do an expect and then just throw in a message that says index out of bounds. Cool. Let me think. Is this going to handle all cases? It handles the none case. But I don't know if it really handles. Yeah, it doesn't really handle. If what we're asking for is out of bounds. I mean, let me think of where this would not work, right? Oh my god, I did it in the wrong place. That's really funny. Okay. I meant to do it here. Do I get that paste? No, that's okay. Okay, so then our test should end up just giving us a panic with index out of bounds. Nope. You called option unwrap at 151. When did I do this? 151. Okay. Oh, it just isn't giving me the backtrace. That's interesting. When did I unwrap? Before this. Oh, right there. Duh. Okay, yeah. So this isn't good enough, right? So yeah, I guess we should do that. We'll leave that there for now. And here we'll do if let sum head equals self.head, then we do this, else actually I guess we could actually do this. If self.head is none, we know that index is out of bounds. Index out of bounds. I actually like that better for now. We'll go back to this, delete that. And I mean, obviously this is a little extra right now. We could probably clean it up a little bit. Okay, we expected that to fail, but we should actually get a panic. Yay, we got a panic. Okay. Yeah, that's fine. And then I think we can go here and say panics if index is out of bounds. I wonder what vec does. Let's see what vec does when you go out of bounds. I'm guessing it just panics. Yep. Cool. That works. I guess they like the lowercase panic message. Sure. Why not? Okay, so let's think about this. We handled if head is none, which would mean that we have no length. We handle if this is a null pointer. We just say index out of bounds. But I think let's see. I mean, is the pointer guaranteed to be null just because it's outside of our contiguous memory? I don't think so. I don't think so. So really what we should do then is do an extra check here, just to be safe, which is going to say if offset is less than self.length, then we can do this, right? Else, we're gonna panic and say the same thing, index out of bounds. Whoops. So this is going to be different. This is going to be NPE. How? We'll just do that. Okay, sweet. So we know we get a panic if our index is out of bounds. All good. And we see index working, and we can also, I think probably the most interesting use of index would be down here where we have a bunch of elements, and we can say assert eq. What do we have? We have 5 elements. I mean, we pushed 6, but it overwrote 1. And you know, again, this is another way we could have tested that our overwrite was working, is that we should have our 0 should be 10. And let's see about, we know we've also wrapped around, so we can check our tail to see what the wraparound is. So let's see. So that means that if we're pushing to the front, oh yeah, 10's not R0. 10's actually, I'm being silly. This should be negative 2340. Okay, negative 2340, yes. And then assert eq 10 should actually be R4, which is our last index. And if I have my mental model correct, we'll just at least test it out, that R3 should also be wrapped because of where we start putting these elements. But also print out what our head and tail is, just to be sure that we have it, that we're thinking correctly about all this. What was I doing? 7. Okay. And before we do all that, let's just do a debug print of r.head and r.tail. Oh, we got a failure. Interesting. It's unexpected. Index out of bounds. Might have made a mistake in our implementation. One second. I have to check messages. All right, cool. All right, one other place. One other place. Let's see. Cool. Okay, let's see where our mistake is. Let's get rid of these warnings since we're not using dref. And then I'm confused as to why I'm not seeing my prints here. Oh, wait, no, this would be right. 15R0. Wait a second, so I must have made a mistake. If offset is less than self.length, does that make sense? Let me just think about this. Nope, that doesn't make sense. That's funny. Yeah, because our self.length would be, let's see, our offset would be like 2 and our self.length would be 1 in this case. Because it's either 2 or 3 is where it's going to write to at the beginning. It's funny. Okay. I'm glad I didn't just check the other one because that would have possibly screwed me up when I was at full capacity checking. Okay. So this is good to have here. So if offset is less than self.length, no. If offset, I mean, obviously we know if offset is less than self.capacity or is more than self.capacity, greater than or equal to, we would know that it's absolutely not working. Like completely off. But we want something better than that, right? Because we don't want them to read something that they didn't push there. So we'd basically have to say let's see, our head offset is already there. Oh, why am I having such a hard time with this? I just need to write it out. That's why. Okay. So in our example, all right, let's just start with a new example. let's say we have this, right? In this case, self.head equals 2. And our offset, when we put in 0, would equal 2. Our length would be 1. Our cap is 5. Oh, it's 6. Let's make it 5. Okay. Our cap is 5. Right, so to determine whether the index is in bounds, oh, it's just if index is less than self.length, not the offset. That's where I was wrong. Duh. I can just do it like as if it was a normal vec. I can just pretend because the index they're passing me has that relationship with length. Oh dear. That's very silly. Very silly indeed. Okay. So let's get rid of our debugs and our tests. And then the other thing I was interested in is kind of wondered how this worked with boxes. I'm trying to remember why I am wondering how it works with boxes, but let's see. Why do I think it would be any different? Do I have a reason for thinking that this is different? No, not really. I mean, we might as well try it just to make sure that we're not like totally off. But yeah, we might as well. Right? So we have 1, 2, 3, 4, 5, 6. We just popped off hey. No. You're completely wrong, Engineer. I'm just messing with you. I don't know why I never did this before. I mean, you are wrong, but I was just messing with you. There. I've been meaning to add some new people here. There we go. So actually this is just in a test and I used a box. So in this case, this is just a RingBuffer of boxed strings. It's not actually part of the RingBuffer implementation. I wanted to do this because box requires a drop since box is a pointer. So box moves something from the stack to the heap. So I wrote this test so that I could prove that we don't have a memory leak. When, and then I'm dropping all of the allocations properly. So that's the point of that test. But in this case, I'm not using a linked list under the hood for the RingBuffer. I was just about to, let me write this one thing and then I'll show you the glory of the ring buffer we have created. I just need to write a test, just making sure that the index that I just created, implementing the index trait works as expected. So let's go in honor of end is near, we will do Guten Tag, which I certainly said perfectly, no doubt. So that should be at index 2. So let's see, if we just do R2, nope, be nice if I knew how to type. It'd be nice. And R2 should be a box new Guten Tag dot to string. Might just have my types wrong. Oh no, that works. Cool. Yeah, I guess that's kind of how you would think about it, right? I mean, it'd be interesting, like, to implement a ring buffer with a linked list. You'd basically have to do it in a way where I mean, you could just write like is a circular linked list like an actual thing? I've never actually looked it up. I mean, it would be easy to write. You just basically check, like, is this my tail? If so, just circle back to, yeah, it is a thing. Just circle back to my head. You could easily, yeah, you could easily write it. I mean, it'd be easy to write in general, but I could even just like change my double linked list to be like, to have a circular implementation, like fake it. Yeah, cool. Oh, that's what happened. I was like, what is this thing on my feet? And it's that my foot thing. I have a footrest and it has apparently broken somehow. Some glue has come undone because I probably rubbed against it too much. Okay, so yeah, I think I might be done. I think, as in, I don't know if I'm going to do anything else for the ring buffer. I'm pretty happy with where it ended up. So our ring buffer has a pointer, since we're using an actual contiguous memory block. It has a pointer, it has a head and a tail. Those are just the indexes of the head and tail, a capacity for our underlying memory, and a length. We allocate our underlying memory. I think you were here on Sunday when I got there. It did get a little bit rusty, but in a good way. In a good way. All right, so we allocate our underlying memory with this right on when we construct. Our length is 0, our head is none, our tail is none, right? But we'd still have a pointer to where our memory block starts. In push front, it's pretty simple. We check if there's an overwrite. This is where we are being kind to our memory. And if our type needs drop, like that box does down there, we're actually making sure that we call drop on that value, which will free up any memory that it points to as well. Basically anything that it owns that's not within our contiguous memory block. And then we overwrite tail. We do our bookkeeping. and then that's push front. Pop back, am I peaking? No, I'm not. I keep thinking I'm peaking. I don't know what it is. Maybe it's just the sound of my voice that's bothering me. What the hell is this song? It sounds like a really quiet Seinfeld, like gone wrong. I don't know. Not down with it right now. Okay. Yeah, it has gotten easier and easier. I mean, that said, I did a 4-hour stream on Sunday where I was just like, I wouldn't say I was like banging my head against a wall, but I was definitely, it took time, you know, like just like processing how I was actually going to do this, and also understanding more about ring buffers because I never really played with them before, you know. So there's that too. Pop back is pretty simple. We're reading what's at the tail, and then we're updating the tail to the thing that was before. So this is what I did today. Is I started with a deref implementation, which allows for a slice, but that doesn't work because slices in Rust are basically a reference to a contiguous memory block. And even though we have a contiguous memory block, the elements, like the actual values, are not necessarily contiguous, right? So I can't make a slice of 4 blocks of memory here and 2 blocks of memory there, right? I can't do that without including the whole thing. But if I sent that to a user, they would be confused because all the indexing and ordering and everything would be wrong, right? So, so then I implemented the index trait, which is pretty cool. One of the things I like that's cool is that index is just a trait, and what that allows is this kind of index access syntax. So this is just syntactic sugar over the index trait. And so even though I implemented this data structure myself, I get some of those cool looking, you know, easy ergonomic syntax for free just by implementing index. And then of course that also gives me kind of like a get for free, you know, an access. The only difference really between like a true get that would give you a reference in this is that it actually copies the value, but that's okay. Yeah, exactly. You just drop the oldest data. I forgot to go into my other cool use case that was brought up by chat on Sunday. Vivax, who hangs out in chat a lot, mentioned that they use ring buffers for slow motion cameras. And the way that it works is it's actually always recording the frames for slow motion. And then when you press the shutter button to actually do the capture, it is after it's already captured everything, right? And I thought that was like one of the easiest ways to understand both like how a ring buffer works and a really practical use case for it, right? Because all you care about are the most recent frames in that scenario, and you can just keep overwriting all the time. And obviously that's a really you know, it's a lot more efficient, obviously. So use it in UDP. They might. I wouldn't be surprised. It makes sense. It makes sense to me, but I'm not great with my network protocols, to be honest with you. I'm not super good with them. Oh yeah, that would make sense, right? Because you're kind of getting more of a streaming type channel going on. Yeah. I could see that. Cool. Well, I'm pretty happy that we were able to do index. It gives us at least something. It doesn't give us a lot, but it's like a nice rusty way to give us access to the elements in the array. So we didn't get as thick as I was hoping with dref, which would have given us a slice, which would have given us so many methods on slice that you can do. You can do sort, you can do all these crazy things. But index is still cool. There is an index mute. So we could do that real quick. I don't think it would be much harder than what we already did. Let me just look up the basics of that one. Might as well do it while we're here. Okay. Maybe I can actually get my LSP to work. It's getting there. It's thinking about it. It's really this slow, yes. It's actually this slow. Really? Is that all you got? You're not actually thinking about it? How about there? Can you do this for me? Really? Can't even do that? Okay. Okay, so it brought an index mute, but it didn't like give me my trait impl for free, which is annoying, but okay. So we have to specify that the index, it's indexed by usize, and we'll just do RingBuffer. Yeah, this is why I don't use it. It's too slow. I could have typed that out. I don't think... Is this how I do it? Oh yeah, there it is. Okay, okay. That's not so bad. I like that. Okay. You know what? That wasn't bad. If I just type out the first line, it can at least give me the function I need to implement. Yeah, that's not bad. Oh, that does actually remind me that I did the other thing wrong, I think. Oh, really? So you don't have to do that. I'm guessing it takes the output from the index above, and that's why that works. And I'm also guessing that I was supposed to, instead of this, do... actually, I should be able to just say output. No, I can't do that. Okay, I do have to say self. Okay. Alright, so this gives me a mutable reference to self output. I think it's going to work very similarly to our other one. So let's just start by copying that, and then we'll go from there. Okay. So part of this is correct, but right. So instead of as ref, I think it's literally going to be I think it's literally this. How awesome would that be? Boom. Index mute taken care of. So I'm pretty sure how this works is it just depends on the caller. Let's play around with it. These tests are getting pretty gnarly because I'm doing a bunch of things at once, but that's fine. Let's do, yeah, let's do no one. What do we want to do? We can do an eye size again, that's fine. Yeah, no, that's fair. That's fair. All right, I don't really care what my capacity is that much. Let's just do an r.push front 24. Okay, and then let's see, -20 and 245, sure. Okay, so we have 3 elements in our ring buffer. Yeah, exactly. I mean, it's just for learning, right? We have 3 elements in our ring buffer. What we should see if we actually have, I wonder how mute works. That's what I'm wondering. So let mute equals R2. This should be 24. So we're going to start with assert eq 24, comma 24. Make sure this is correct. It is. Now oh, wait, does this mean that I can do this syntax? I think it might. Okay, I think that's... Oh god, I didn't assert eq 24, 24. That's really funny. I meant to do this. R2 equals -45. Assert eq -45 R2. No way, that's so cool. That's pretty sick. That's pretty sick. Because I pass it a mutable reference to the underlying data, I can then use index syntax to make changes in... I mean, I knew there was something along these lines, I just didn't like put it together till I wrote this test, which is why I wanted to write it. So since -45 is actually our last element, it should be what we end up popping off the back. Boom. Hey, that's pretty cool. I like it. Index and IndexMut. Pretty neat. It's really nice when you have like nice syntax for things that are actually available to custom types. It is definitely something that makes the language more fun to work with, no doubt. So I'm really happy with that. I'm pretty happy with what we did. I mean, yeah, pretty much today all I did is implement index and IndexMut. We also tried the dref implementation just for fun, and then found out it wasn't going to work, which is also fine. Learn things. And yeah, now we have the ability to get into the index. We have the ability to mutate using index logic. We should thus let me think about this. Yeah, we could make a simple. I don't think we can do this. What I don't think index gives us is the ability to actually loop, because we don't have an iter, right? So we can't do, well, we can't do a complete iter, which would be like for enr. We would have to, yeah, there we go. See, you'd have to do an into iterator on that, and I don't think that index gives us that for free. So I don't know. We could say assert true just for fun and let it tell us that we're wrong, right? So while index doesn't give that to us, what we are able to do is say, come on, get in insert mode. 0 ... to r length, and we'll call that an I, and then I'm trying to think of a reasonable test we could do with this. It's fine. We'll just do this. Print line RI, right? Does this work? Oh yeah, duh. This is why I should just do debug. Except then it's going to say T doesn't have debug, but that's whatever. Or no, I think I did derive debug. Yeah, I did. And then just so that we can actually see it without having to go to other stuff, let's just do assert false. And there you go. So even though we didn't implement an iter, we are able to iterate just by using index, right? Like you would for a lot of, you know, it was a little old school, but it's still nice that we have that ability. Cool. So I'm just gonna, I'll leave it in there, sure, just for fun. Okay, that looks good. Let's commit and push. Well, yeah, iter gives you so much stuff. It's not a bad idea. I just don't have time to do it today. But it is probably a good thing for me to do, is actually implement iter for this maybe something else before I move on to trees and stuff like that. Because that's what I was going to do next, is trees. So I'll probably do that next time, is we'll do iter. I haven't done complicated iter implementations yet, so probably a good idea to do that. And also, I mean, this wouldn't be that hard. And then change my get in my linked list to iter implementations, because that would also give us a lot. But yeah, making it an iterator, you can do, you like outside of yeah, we can just do a lot with it. You can do a lot with it with iter. RingBuffer, ample index and IndexMut. Sick. Cool. Well, it was fun. Thanks so much for hanging out and the chats. And Rust has map and reduce. Yeah. Yeah, they do. They call on iters. They do. They call it map and fold. They call it fold, showing their FP roots in OCaml and or Haskell. We did that. We pushed everything. We're working, and that was cool. Yeah. So thanks for hanging out. Next time we'll make this into an iterator and go from there. Maybe just do iterators on this and our linked lists. Maybe we can do it all in the same stream. I don't know. It should be tomorrow. We shall see. So thanks so much for hanging out. Let's see if there's anybody I want to raid. Just raided Eduardo. I'm trying to remember what Christoph does. Let's find out. Oh, he's the Zig guy. That's what Christoph is. He's the Zig guy. I'm a little nervous to raid a Zig guy on with Rust, but you know, I don't know. Probably should just do it. Oh, Leostera. I didn't know Leostera was streaming. I'd rather raid him anyway. He's an OCaml guy. I think it's pretty interesting. So let's raid him. Okay, cool. /raid Leostera. All right. Cool. Thanks, guys. Catch you later.